Okay, we've come to the very last plate tectonic diagram. Now I've saved the most difficult for last. So we're actually going to start this one with a Sharpie, and we'll paint details onto it here in a moment. Okay, so our last diagram is the transform boundary. A transform plate boundary is when two plates slide past each other. They don't collide or diverge, they slide. So we're actually going to do the 3D model with this one so we can see underground as well as what's on the surface. So this one's kind of difficult, so bear with me here. We're going to start with a, let's make it 2-inch wide. Do 3 inches. All right, 3-inch wide line parallel to the bottom of your page, or fairly close to it, right there. Then we're going to go at about a 45-degree angle and go straight up from that. Let's go about 6 inches. Okay. Now we're going to come straight down from there. Let's do 2 inches because that's about how much room I've got. Okay. And come down again on the other side of it. The same length straight down, and then connect this to make a little rectangle. Okay, so we've got the beginning of our block diagram of a transform boundary. We're going to make another line. Let's start with the side. We said 3 inches. So it's not the best ruler for this. We're going to do 3 inches from this corner parallel to the top and bottom of the page. So we're just going to come straight over 3 inches, just like our bottom line was. And now we're going to connect it with a line that's parallel to the other angled line that we did, just like this. Alright, so this makes one block, or one side of our diagram. So this is one plate moving one direction, and then we're going to put our another plate over on the other side. And we're going to start it a little bit above the bottom of that plate. So it has slid up. We're going to make it the same size, so 3 inches. Okay, 3 inches. And it's going to come down 2 inches. Vertical, straight down. Okay, straight down over here. Same amount, 2 inches. Okay, now we're going to connect this bottom straight across. And then we're going to connect these two bottoms here. Okay, the right corner of our left block and the right bottom, or the left corner of the right block. Just follow what I'm doing, not what I'm saying. Alright, so we're going to continue this one. We moved up about 2 inches, so we're going to continue this line out 2 more inches. Okay, and that's going to come over parallel to the bottom 3 inches. We don't quite have 3 inches, so it's going to go all the way to the edge. Okay, and this corner is going to come up to that line we just drew. And we're going to do another one right here, right up to that as well. Parallel with that line. Alright, so now we've got two blocks that are sliding past each other. We're going to make this a diagram with this being one plate and this being the other. So this plate is going to be moving this way. you can see it's been displaced from here to here. So the plate's moving that way. And this plate is going to be moving this way. This will make much more sense when we apply our surface features to this diagram. Now, the most famous transform plate boundary probably in the world is the San Andreas fault line. Now, the San Andreas fault line is where the North American plate and a section of the Pacific plate are sliding past each other. Specifically, the Pacific plate is moving kind of northwest, and the North American plate is moving the opposite direction in relation to each plate. So what happens on the surface is surface features are displaced. Some of the easiest surface features to look at and find displaced are man-made ones, but we're going to talk first about natural ones. So imagine that there's a river flowing, kind of meandering around, and it comes to the fault line. It comes to this place where the block has been faulted. What happens is a really weird thing. We don't normally see 90-degree turns or bends in nature, but along a fault line is one of the weird places that we do. So the river will be displaced. It'll follow the fault line and then continue on our other fault block, our other plate. Now, you can also talk about whether it is a right lateral strike-slip fault or a left lateral strike-slip fault, and that is determined by the relative motion. So imagine you're standing here on this plate looking over to the other, and you notice that the stream from your point of view has been moved to the left. If you're standing here looking up, it's moved to the left. But if you're standing here and looking at it, it's also moved to your left in relation to where it should be. So this would be a left lateral strike-slip transform fault. Now, if our river had come this way and moved up here and came over, then it would have been a right lateral, because the shifting would be a different relation. Now, that doesn't mean that this block stayed still and this one moved. We're just looking at the relative motion when we're talking about that. Okay, so plates that are sliding past each other have these disjointed features. Another thing you can see that kind of thing in is with man-made features. So let's imagine that there is a road, just a road, straight road, man-made, coming right across this section of land here. Okay. If this is an old road, it's been here for several years, the San Andreas fault, it's going to have displaced that road a little bit. Maybe not as much as the river, because the river's been here longer, and the road was put in after that. But the road's also going to be displaced towards the left. Okay, so same displacement, because the fault is always moving in that same relative fashion. Okay, so there's our road. Maybe next to that road, we have some fence posts. You'll often see in pictures of the San Andreas fault line displaced fences. Some of the weirdest features are man-made and displaced from that fault. And sometimes this can happen overnight with an earthquake that's strong enough to displace these features. When that fault block slips and releases that pressure, and an earthquake happens and the rocks move. Or it could be gradual, and you never even perceive that motion until you see these displaced features. So let's put a little, maybe there are a set of telephone poles. That'll show up a little bit better on our diagram. And of course, these aren't to scale. This is just to show this process. The point, though, here is that everything is going to be displaced in the same direction. Now, I won't fault you for liking the San Andreas movie that came out with The Rock a few years ago, but the things that you see in that movie would never happen on the actual San Andreas fault line, because this is a strike slip transform boundary. There's a scene where they're driving along a road like this, and they all of a sudden they have to slam their brakes on because there's this giant gaping gash in the ground where the ground opened up. That wouldn't happen, at least not at the scale that they're showing in that movie, because it's just a strike slip fault. They're going to displace the features, yeah, but they're not going to fall in a hole or a trench made by the San Andreas fault line. That's just not going to happen. And it's probably not going to displace that much over just one earthquake. Alright, so let's say there's some trees there at the very end. There's a great image that I love to use in my class of an orchard of trees that were planted, of course, by man. So these little trees all planted in a row, and there's hundreds of rows for them. I think it's like a orange grove, orange trees maybe, out there on the coast. And they were planted a considerable amount of time back, and when an earthquake occurs, they start to move. Those fault blocks move, and the trees change position. And there's this whole line, this diagonal line across these nice evenly planted rows that shows the fault moving. Shows how it's moved over time. So let's just put some... These aren't very good trees. I'm no Bob Ross. We're not going for accuracy here. We're going for concept. But it's a really great example of how even our strongest features that we make, and how we change the Earth's surface. The Earth is ever changing. It doesn't care what we do. It's just going to keep doing what it's doing. Okay, so this transform boundary, the San Andreas Fault is known for earthquakes. But the earthquakes that actually happen along the San Andreas Fault are relatively shallow. The earthquakes that happen there aren't very deep, because this deformation happens all the way to the surface. And the earthquakes that happen are very, very shallow. And the earthquake waves kind of radiate outward through the rock, through the layers, on through, and they dissipate over time. There's a scene in the San Andreas movie where the geology professor talks about the earthquake being so strong that it could be felt all the way to New York. That's just not going to happen on the San Andreas fault line. Now, if one of the convergent boundaries, like the convergent boundary that we had in Alaska, where the Pacific plate is diving under the continental plate, forming the Aleutian Islands, all the mountain ranges around the Pacific Ring of Fire, those earthquakes are the mega thrust earthquake. Very, very deep earthquakes that can be felt for very, very far distances from their epicenter. And they cause tsunamis. Another point that I like to point out in the San Andreas movie is they show a tsunami. Most of the San Andreas fault line is on land. Nowhere is it going to be popping up or down to cause that tsunami feature. Now, I guess it could be argued that the earthquake, if it was strong enough, could cause some underwater landslides on the continental shelf that could cause a tsunami. But we're splitting hairs at that point, grasping for straws. It's probably not a good representation of an actual San Andreas earthquake. But it's a good movie, and it's a great movie to point out all of those inconsistencies. Let's put a power line on this. And the power line's got to jump over to the other line because of that displacement. So things like that affect human-made structures, and we've got to change our way of doing things when we come up to stuff like this. Okay? The power of nature is immense, and plate tectonics are probably the strongest and most energetic interactions on the Earth's surface. All right, so that finishes up all of our diagrams for plate tectonics. We'll label these features the relative motion of the plate, the shallow earthquake, the displaced surface features. These are all characteristics of the transform boundary. Okay, so that should finish out your diagram drawings for the plate tectonics section. And this will be the last diagram for a while in the joy of geology. So we'll see. Maybe I'll come back and do a karst diagram or how sinkholes form. We'll see what I can come up with. All right. Hope you've enjoyed it.